Hello everybody. Today I'll be presenting Spanner, which is Google's globally distributed database. This system was developed by James Corbett, Jeff Dean, and about 20 other people, as is common in distributed systems research because the systems are so complicated typically. My name is Joey Vidoweg, and in case you don't remember me from class, here's a picture of me. In this talk there's going to be some distributed systems buzzwords and abstract nouns. I'll do my best to make this not sound like some dumb marketing pitch and to explain the terms as we go along. So here's the agenda of our talk today. First, we're going to talk about why Spanner matters and the problem it solves. So typically, relational databases are easier to scale vertically by adding bigger and more powerful servers than they are to scale horizontally, which is the concept of adding more servers. And so two of our main techniques for scaling horizontally for relational databases, which are replication and sharding, are also hard. And I will explain what replication and sharding are momentarily. But first, let's time travel back to 2006. We are at Google, where they make most of their money selling ads. All of their customer ad data is stored in a MySQL database, which is manually sharded, so sort of split up across data centers around the world, using sort of complicated replication schemes that are done by the application itself, so the ads application itself, rather than some service provided. And so, because of all these complications, doing simple maintenance on these shards of this database once took them 2 years. That whole process was certainly a pain, and they saw a need for an internally provided service that externally facing Google applications could use, such as Google Ads, which is why they developed Google Spanner. And this is the key idea of this talk, and if you remember nothing else, it should be this sentence right here, that Google Spanner provides horizontal scaling of databases around the globe with strong consistency and high availability. And we'll talk about what consistency and availability mean momentarily. For now, just know that they're good things that we want in our distributed systems. So let's talk about Spanner's implementation now. Before we do that, just a quick clarification. The examples we're going to look at use a key value store, which is non-relational data, whereas Spanner stores relational data from the applications that use it. But internally under the hood, to store this relational data, Spanner uses timestamped key value mappings, which is why we're looking at these examples in terms of a key value store. So to turn this key value data into relational data, what we can do is map a primary key, like say this ID, to the data of the columns. As you can imagine, this does have some caveats attached, which we will talk about. So as was mentioned, one of the horizontal scaling techniques that Spanner uses is database sharding. So oftentimes our database can be too large to store on one server, or at least too large to store efficiently on one server. So typically what we do in that case is we split up the assignment of portions of the database to different servers, which helps decrease the load to each server, which improves the latency of our service, which is how fast we can service requests, as well as the availability of our service, which is whether we can service requests or not. This availability is improved because if one of these servers goes down, the other can still serve its key range. The main downside of sharding is that it adds increased complexity to our application and is difficult to manage. One thing sharding doesn't provide, though, is fault tolerance over the entire key space. So if our only replica on the left here goes down, it gets sick and has to self-quarantine and can't service requests anymore, ideally we would have this machine replicated so that we could continue to service requests in the event of a server failure. And typically we accomplish this replication via an algorithm known as Paxos. Paxos provides the guarantee that so long as a majority of these replicas are functioning, we can still accept requests, which improves the availability of our service and that we can continue to accept requests over the whole key space in the presence of failures. But again, our main difficulties are that this scheme is difficult to manage, and we've also introduced some additional overhead in needing to copy values between these replicas, which can harm latency. More on this in a little bit. Because each technique has its own benefits and trade-offs, we often end up combining the two in real-world systems, like Spanner. We shard the key space among Paxos groups to reduce the load to any one Paxos group, and we replicate the shard within the Paxos group to achieve fault tolerance for that shard. And combining the two, we gain fault tolerance over the entire key space, as well as improved throughput and latency for the service. So earlier I mentioned that one of the downsides of replication is that it can harm the latency of our applications. And this mainly has to deal with consistency. So what is consistency? Consistency refers to whether the answers we ask of our system make sense, and if not, how long it takes for them to make sense. And to illustrate this, let's take a look at an example of two operations which will be executed serially, so not in parallel. Our first operation is going to be a write to the first key on the first server, and then right after, we are going to read the same value, or the same key from the third server. And our answer here of what v ends up being depends on our consistency model. If we wait for the write to propagate to the third server and choose the sensible answer, we would get v8, and this would be known as a strong consistency model. Whereas if we wanted the quick answer, we would get v1, which would just be the value that server 3 had at the time, without waiting for the value to propagate. So now that we know what consistency and availability are, I'd like to reiterate the key idea of this presentation again, that Spanner provides horizontal scaling of databases across the globe with strong consistency and high availability. And it was previously considered impractical to achieve both strong consistency and high availability at global scale of replication until Spanner. There had been other systems that have achieved these two, but just not at a global scale. So let's look at how Spanner achieves strong consistency. In order to achieve strong consistency, we need an ordering of events. Ideally, this ordering would be the real-time order that they occurred. An event here could be a regular read or write, or a transaction, which we'll talk about in a little bit. So our intuition might tell us to use logical clocks, or something that can't be affected by clock skew, but the unique approach that Spanner takes to determining a total ordering of events is the solution called true time. So true time is an API offered by time servers to shard servers. These time servers provide an error-bounded timestamp to shard servers. They do this by utilizing GPS signals and atomic clocks. There's two kinds of time servers, one that uses GPS and another that uses atomic clocks. And these time servers try to bound the potential clock skew and the network latency to sort of calculate the uncertainty of what time it is. And these time servers frequently communicate and synchronize with one another to get a good reference and to tell whether they are very far off or not. So as we can see here, true time, by asking for what time it is now, the true time API provides a range of times, which is the earliest time it could be and the latest time it could be, which incorporates a certain amount of uncertainty. So Spanner uses true time to store multiple versions of the keys, as we can see here in this example. Up to a certain point, when there are too many versions of a key, older versions will be garbage collected. Each update to a key adds a new version of the key with an updated timestamp. And this allows us to specify whether we want to read an older version of the key or the most current version of the key in our reads. And as I said, writes will update the timestamp of a key, as shown in this example. And since again these are a replica group, this update will propagate to the other replicas. And so one thing I wanted to point out is that the read and write we just looked at touch separate shards, and they're their own operations. But oftentimes it's necessary for us to coalesce our data across shards, and this is accomplished through a convenient abstraction known as a transaction. In this transaction, we're going to read the value of a key from one shard and then write that value to another shard. And this would be an example of what's known as a read-write transaction. Supporting transactions is crucial for the usability of our distributed database because they are so convenient. Another example of a transaction would be a read-only transaction in which no writes occur. In this transaction, we're going to basically just take the sum of all of the values of the keys. One of the main challenges in supporting transactions is maintaining strong consistency. Normally, we wouldn't be able to run these two transactions in parallel because we might get incoherent results for this transaction if this reading and writing transaction didn't finish. And so because of this, we would have harmed latency, which is a factor of availability, since each one of these transactions might have to wait for the other to finish. And normally this waiting is accomplished by a mechanism known as concurrency control, which refers to sort of locking around the data that a transaction accesses. But true time allows us to run these transactions in parallel without concurrency control because the transactions themselves and the key versions that they access are timestamped. So we can order the transactions accordingly and determine which versions of the keys the transactions should see. As we see here on this slide, Spanner does support both kinds of transactions we talked about, as well as snapshot reads, which are reads of older versions of a key. And Spanner does use concurrency control for read-write transactions if two rewrite transactions were trying to run at the same time to ensure consistency, but all other operations can be done without locking or concurrency control, which improves the availability of the service. And timestamps are utilized to achieve this consistency, and we'll talk about these replicas required momentarily. Before we do that, let's take a quick look at how Spanner represents these shard servers, which it refers to as spanservers. So spanservers store the data of Spanner. They store those key value mappings in a data structure known as a tablet, which is just a large bag of these mappings. A tablet is a large shard of the entire key space, so it's not the entire key. It does not store the entire key space. These tablets themselves are stored on top of a distributed file system known as Colossus, which is the successor to the Google file system. In typical operation of the Paxos algorithm, a leader must be decided upon every update to the replica's state. But Spanner utilizes a variant of the Paxos algorithm where the leader is decided ahead of time and remains the leader for a longer period of time rather than upon every update. Doing this allows us to reduce the total round-trip communication and allows updates to be processed quicker because less communication is required in deciding the leader. This pre-designated leader acts as this replica group's transaction participant in the event that this shard group needs to be a part of a transaction that involves it and another shard group denoted in green here, and this shard group is denoted in purple. Now that we know what each type of replica is and what they're made of, let's take a look at who needs to be contacted for each kind of operation. So for our transactions, we first have to contact the transaction leader, and for our snapshot reads, we can contact any up-to-date replica. Up-to-date refers to if this replica had been offline for any period of time, either due to being recently added or a crash, it might need to catch up on updates. And so normal writes, which are writes that only affect one shard group, are also implemented as rewrite transactions, but just to one shard group. And standalone reads, which are not snapshot reads, they ask for the most up-to-date data, are implemented as read-only transactions, but they're still performant because they don't require any concurrency control. So up until now, we've looked at the shard servers or span servers themselves, but typically there's administration that happens on top of them, such as assigning the shards and moving the shards around. And this is where the concept of a zone comes in, which is the Spanner's administrative unit of deployment. Replication happens across these zones, and these zones can either be in the same data center or a different data center in a different portion of the world. The application gets to decide these replication parameters. And so to illustrate what a zone is, it's as simple as where each of the replicas in a replica group resides. So in this picture, to illustrate, we can have these two zones be in the same data center, so US East, and this zone could be in a separate data center, but each of these zones and the span servers in them makes up a replica group. And Spanner also introduces the concept of a directory, which is Spanner's unit of data placement. They are smaller shards of the key space than a spanserver's tablet. In fact, they are a subset of a spanserver's tablet, meaning that a spanserver can store multiple directories. A directory is also a bag of these time-stamped key value pairs. We can think of directories as a continuous section of rows in the database, and directories are what are replicated across zones. This figure here showcases directories being replicated across zones as part of a Paxos group. And most of the examples we looked at, a replica group only had one shard in it, but Spanner supports having multiple shards, or these kind of directories, in Paxos groups. So a group, as shown in here, can have more than one directory in it, and they can also be moved between Paxos groups too. And tying it all together, our spanservers are located in zones, and these zones are administrated by what are known as zone masters. Zone masters are what assign data to spanservers, and spanservers serve this data to clients. These other components of Spanner were not mentioned in detail in the paper, but they serve important administrative tasks, and if you're curious what they do, you can read about them in the paper. So now that we know how Spanner works internally and how it's organized, let's take a look at the main caveat that applications face when wanting to leverage the benefits of Spanner. This main caveat comes about when we try and create this abstraction of a directory. So in our typical relational tables, we can think of these tables as sort of separate concepts that might relate to one another. So like the rows of this album table relate to the rows of this users table. But in order for Spanner to know the locality of data and know how to replicate things and how to create these directories, Spanner requires applications to modify their SQL code in their tables to form what are known as these kind of interleave tables, using this interleave in syntax. And this allows Spanner to know what an application's directories are and how to replicate these directories. And yeah, this is the main downside of Spanner, that we have to modify our existing SQL code. Alright, and now to wrap things up, let's take a look at Google's initial evaluation of Spanner. Their first evaluation was some micro benchmarks that were run to try and determine the overhead of Spanner's call stack for things like standalone reads and writes, which are reads and writes that don't necessarily touch more than one shard. And so the key takeaway from these micro benchmarks is that adding replicas did not significantly harm the latency of reads and writes, while also improving the throughput of reads significantly and writes slightly. And adding replicas only harmed the throughput of writes slightly between 1 and 3. The next experiment they ran was to determine the latency of transactions which touch more than one shard. A quick clarification, two-phase commits are a form of concurrency control, which is how we maintain consistency in transactions. The key takeaway from these experiments were that transactions can scale up to 100 participants of replica groups, where the tail latency, the sort of 99th percentile of how long it takes transactions to run, is still somewhat reasonable, around 100 milliseconds. The next experiment they ran was to try and determine the average time, the average amount of uncertainty that true time timestamps come with. And the takeaway from their experiment, which sampled these timestamps and their uncertainty over about 4 days, was that around 99% of the time the uncertainty is less than 3 milliseconds, and around 90% of the time the uncertainty is on a much smaller scale, around the order of microseconds. They did observe some sort of tail latency, where about 0.1% of the time the uncertainty can range up to 10 milliseconds, and at the time of the paper they said they would investigate why this would happen. But even still, 10 milliseconds is not all that long to wait to outweight the uncertainty of a timestamp. In this experiment, they evaluated the availability of Spanner in the face of entire zone failures. So in this experiment, they set up 3 zones, One zone had all pre-designated leaders, and the other two zones just had the regular replicas of their respective replica groups. 5 seconds into this experiment, one of the zones was killed, and these failures were simulated in 3 different ways. One was where a zone with entirely made up of non-leaders was killed. Another was where the zone containing the leaders were killed, but the other zones were notified of this, which is leader soft. And the final run they did was where the zone containing all the leaders were killed without notifying the other replicas in the other zone. And this was the run, this leader hard run, was the only run where they saw a dip in throughput and availability. And so the main takeaway from this is that killing an entire zone does not harm the availability of Spanner, is what they saw in this experiment. And to wrap things up, I think the biggest testament to Spanner's evaluation is that Google has continued to use it for around 8 years now, since this paper was released in 2012. And during its use, they've seen around 5 nines of availability, which means that the service is really only down for around 5 minutes every year. And it's definitely a testament to Spanner's effectiveness that the Google Ads backend F1 still uses Spanner. And they've had such a good success with it that they're now offering it as a part of the Google Cloud platform, which any of us could use or any of our companies could use. So hopefully now you can explain to them how it works. And just to reiterate the key idea of this presentation one last time, Spanner provides horizontal scaling of databases around the globe with strong consistency and high availability, especially relational databases. So thank you for listening, and if you have any questions, feel free to ask, and I welcome any feedback. Here are the references I used to make this talk. I'd especially like to give a big thanks to Professor Matiasta. We went over Spanner in EECS 491 last semester, and the presentation he gave was very helpful and was a valuable resource. So thank you, Professor. I would now like to pose some questions that will aid our discussion of Spanner. So I'd like to ask what you thought were some of the strengths of Spanner's design in the system as a whole, and these are some of the things that I came up with, and feel free to pause the video. I'll also post the slides so that you can take a look at these after the fact. I'd also like to ask what you thought were some of the weaknesses of Spanner's design, and again, here are some of the things that I came up with. And I'd also like to ask what are some design hints you thought Spanner utilized, and here are some of the ones that I came up with. And here's some more design hints I thought Spanner utilized well. And I also wanted to ask what design hints you thought Spanner contradicts. I additionally wanted to ask about your thoughts about the paper itself and what you thought the strengths of the paper were. And here are some of the things that I came up with, as well as what the weaknesses of the paper were. So yeah, thanks again.